Hi, this is Jay. In this video, we will be studying about memory page replacement policies. In order to understand these policies, let us first take a look at paging. Paging is a memory management scheme that permits a process's physical address space to be non-contiguous. The basic method for implementing paging involves breaking physical memory into fixed size blocks called frames and breaking logical memory into blocks of the same size called pages. When a process is prepared to start, its pages are loaded from their source into main memory frames, a file system, or the backing store. The backing store is organized into fixed size blocks, the same size as main memory frames or clusters of several frames. These pages are placed into empty frames even if they are non-contiguous. Here you can see we have our logical memory and physical memory. A logical memory has 4 pages and physical memory has 8 frames. So we have page 0, 1, 2, and 3. Here is our paging table. Paging table is used to map a page to a frame. Here we have our page indexes and here we have our page numbers. So page 0 is mapped to frame 1, page 1 to frame 4, page 2 to frame 3, page 3 to frame 7. And as you can see, these frames are non-contiguous, but we have placed all 4 of our pages into these frames. Now let us see why we need page replacement. Using virtual memory, we try to accommodate the greatest number of processes in the main memory. We can't place all the pages of a process in the main memory at the same time. We place the pages which are needed for the completion of the process in the main memory. To tell us about the demand of the pages which are needed, CPU sends a reference string which contains memory spaces. What happens if the main memory is full and we need a new page? That's where page replacement comes into picture. We have different policies which we use to swap out an existing page in the memory with the one which is currently needed. When the CPU demands for a page and it's not present in the main memory, it's called a page fault. When the needed page is present in the main memory, it's called a page hit. So here are the 3 policies we will be discussing in the video. These are the most popular ones: first in, first out, or FIFO, optimal page replacement, or OPT, and least recently used, or ARU. Sorry, LRU. So let us first take a look at first in, first out. According to this policy, we replace the oldest page in the memory with a new page. It's a very simple policy, easy to implement, but it's not very efficient. It also suffers from Belladie's anomaly. If we increase the number of frames, logically the number of page hits should increase. For some reference strings, when we increase the number of frames, the number of page faults also increases. This is called Belladie's anomaly. Then we have optimal page replacement. According to this policy, we replace a page present in the memory which is not in demand in the future for the longest period with the new page. Then we have least recently used. In this policy, we replace a page present in the memory which has not been used in the past for the longest period with the new page. Now let us understand these policies with the help of a program. Okay, so here we have these addresses. Now let us run them with the policy FIFO. And just for the sake of example, I have set the number of page frames as 3, and we will be drawing comparisons between the 3. So I have kept the frame size constant for all 3. So let us see for policy FIFO. Okay, so what happens is first we get 7, then we get 0, which is again a miss, then we get 1, which is again a miss. So now the number of page frames, we have reached the maximum number of page frames, 7, 0, and 1. As you can see, the first one which was in was 7. So what we do, we replace 7 with 2. So we get 0, 1 and 2. Then you can see the first one which was in was 0 and we got 0. So it's a hit. Then we have 3 which is a miss. So we will be replacing 0 with 3. So we have 1, 2 and 3. Then again, the next element in the reference string is 0, which is a miss. So we will be replacing the first n element, which is 1. So we replace 1 with 0. So we get 2, 3 and 0. Then we have 4, miss. So we replace 2 with 4. So we get 3, 0 and 4. Next we have 2. So which is again a miss. So we replace 3 with 2. So we get 0, 4 and 2. Then we have 3, a miss. So we replace 0 with 3. So we have 4, 2, 3. Then we get 0. Again a miss. 2, 3 and 0. Then we have 3, which is a hit. 2, which is a hit. So the main memory is not updated. Then we get 1, which is a miss. So we will be replacing it with the first n element, which is 2. So we replace it with 2. So we get 3, 0 and 1. Then we get 2, again a miss. So we replace it with 3, 0, 1, 2. We have 0, which is a hit, 1, which is a hit. Then we have 7, which is again a miss. So we will be replacing 0 with 7. So we have 1, 2 and 7. Then we have 0. So we will be replacing 1 with 0. So we have 2, 7 and 0. Then we have 1. We will be replacing 2 with 1. So we have 7, 0 and 1. As you can see, the number of hits is 5 and number of misses is 15. So our hit rate is 25%. Now let us try the same string with the policy optimal page replacement. Here we can see that the number of hits has drastically increased and our hit rate has gone up to 55%. So first we get 7, 7, then 0, then 1, 7, 0, 1. So we have reached the number of maximum frames. So we'll be swapping out the number which is the rightmost in the reference string and we'll be replacing it with 2. So we swap out 7 with 2. Then we get 0, hit, then we have 3, a miss. So as you can see, 1 is the number which is the rightmost among the 3. So we swap out 1 with 3. Then we have 0, 2, 3. So 0, hit, 4, a miss. And 0 is the number which is the rightmost in the string. So we swap out 0 with 4. And we have 2, hit, 3, hit, 0, a miss. So 4 is the number which is not there in the string. It is not in demand in the future. So we swap out 4 with 0. Then we have 3, hit, 2, hit, 1, miss. We have 3 and we don't have a further demand of 3. So we swap out 3 with 1. Then we get 2, hit, 0, hit, 1, hit. Then we have 7, which is a miss. And the numbers we have are 0, 2, 0 and 1. 2 is not in demand, so we swap out 2 with 7. Then we have 0, hit, 1, hit. Next, let us take a look at LRU for the same reference string. Here you can see the number of hits has decreased from optimal page replacement, but it is higher than first in, first out. And our hit rate is 40%. So in this policy, we have 7, 0, 1, and we get 2. So the one which is least recently used is 7. So we swap it out with 2. Then we have 0, hit, 3, a miss. 1 is the number which was least recently used. So we swap out 1 with 3. Then we have 0, hit, 4, a miss. 2 least recently used. So we swap it out with 4. Then we have 2, miss. 3 least recently used. We swap it out with 2. Then we have 3, a miss. We swap out 0 with 3. Then we have 0, a miss. We swap out 4 with 0. Then we have 3, hit, 2, hit, 1, a miss. Least recently used number is 0. So we swap it out with 1. Then we have 2, hit, 0, miss. 3, least recently used. We replace it with 0. Then we have 1, hit, 2, 7, miss. So we swap out 2, which was least recently used, with 7. And we have 0, a hit, 1, a hit. So we can draw the comparisons between the three, and we can say that optimal page replacement is the most efficient policy among the three, and LRU is more efficient than Fifo. Now let us take a look at Bellidy's anomaly in Fifo. So I have set the policy as Fifo, and the number of pages is 3 for this reference string. As you can see, the number of hits is 3. Hit rate is 25%. But what happens if we increase the page number? The number of pages is 4 now, and you can see the number of hits has decreased, and the hit rate has gone down to 16.67%. This should not be happening. That's why this is an anomaly. That's all for this video. Thank you.